Okay, layout team. Basically today I just want to go over some stuff and show you guys what kind of tools we're going to be using and generally what the flow is going to look like. So last meeting, I talked about these three different tools. I talked about OpenSTA, and that's basically our static timing analyzer. And so what that does, it needs all these types of files, and it generates, a lot of different data for us, talking about the clock paths and the worst path and all this stuff. So very useful for us to actually see how our design is going to map out physically and see how the clock is going to be able to propagate through the design. Um, this is Yosis, and so this is our synthesis tool. Basically, synthesis means we're taking our RTL and we're synthesizing something with it. And so what that's going to mean is this tool takes our RTL, it maps it into this big abstract syntax tree, and then it maps all the transistors to that syntax tree. Um, so yeah, pretty cool. Was developed by this guy when he was really young. So yeah, check it out. And then OpenLane is huge. Basically, it's like this giant Python flow that stitches together all these different tools. So very useful for us as ASIC designers because we don't want to have to like individually use all these tools all the time. We want to just run the flow. Um, and so we'll definitely be using this tool a lot and making design configuration files. So all these sorts of things we'll have to specify when we need to. And yeah, so let's get into an example. So in CARP tools, I have these examples in here, and I'm going to run CARP. Okay, so I'm going to go into my examples, and I'm going to go into the comparator. Okay, so this comparator has runs, it has scripts, sim, synth, RTL. So what this means is it has RTL, so it has a system verilog file. It has a run or runs, so it has basically a bunch of output from the ASIC flow. It's got scripts, and so that's a bunch of stuff that I've configured and other people have configured to help us automate things. And we're going to put our scripts that we pass the tools in the scripts folder. We have simulation, so that's just where we put our test benches and our test bench folders. And we have synthesis, and so this is where all of our synthesis results are generated. And so if we go into RTL, let's check out the comparator. Nope, let's read that. So you can read it. It's a basic comparator. Takes A and B and it compares them unsigned. And if it's less than, outputs 1. If it's greater than, outputs 1. If it's equal, outputs 1. Um, so yeah, and then basically what we can do from this is we have this configuration file. And so I'll read you guys that. And this configuration file is pretty simple. It just specifies the design name. And so if you go in here, that's the module name. That's also the folder name. So we keep everything pretty clean. The design name, I put the Verilog files. So inside RTL, we had this file. And then I specify some other basic stuff that you'll need to get through the flow. And so first I can run the flow by running make openlane. I need this configuration file to be set with these variables, and I need an RTL design inside RTL. And when I run this, it runs through the 78-step process. And this is a relatively small design, so it's going to go like really quickly. But you guys will have to know that for bigger designs, this thing could take hours. So just be aware of that. Don't start this when you have to go anywhere. Don't start this on your laptop when it's about to die. And just know that the more tabs you have open while you run this, the slower it runs, depending on your design size. Right now, it doesn't really matter because such a small design. Bigger designs, you definitely want this to be the only thing running on your computer. Um, and you can do interesting stuff in the operating system to give this more compute power, and we can talk about that. But as you can see, it's going through these various steps. First, it went through linting, and then it went through synthesis, and now it's going through all these various steps to make sure the ASIC is actually going to be okay when it's manufactured. Um, and so yeah, it's right now doing the GDS2 stream out, so it's basically making our whole chip file and outputting all that. So yeah, this whole thing takes a while. Like I said, this is probably the quickest you'll ever see it get done because this is a very relatively small design. Now that we have this done inside this runs folder, so if you haven't run make open lane yet, you probably won't have the runs folder, but we can go into runs and we can look, and I have a couple runs because I've been running this, but we can go into recent, and that's a symbolic link to the most recent run. So whenever you create a run, recent is a symbolic link to the most recent run. So you can always just look in recent for your files. So we'll go into recent, and when I look at recent, we have every step, individual step laid out as a folder with information inside of it. So there's very interesting stuff inside these folders. Like for instance, we can look at the synthesis, or we can look at other stuff to look at maybe the net list that got generated. But let's look at the pre-place and route static timing analysis. So this is static timing analysis pre-place and route. So let's look at that. Oh. So yeah, it's easier if you just go type the number, press tab, it'll autofill. So now, so now we're in pre-place and route STA. In here we have this file called summary report. I want to read that to see what it says. And it looks like we had no total negative slack, so that's good because any total negative slack means we're going to have to lower our clock frequency. And our setup worst slack is positive, so this means we can increase our clock frequency. But if you look, it tested various corners. So it tested different transistors, and it tested this typical corner for 25 degrees Celsius 1.8 volt transistors. It did the slow corner and the fast corner. And so if you look at this, you can actually see for the typical corner, it had better slack, but for the slow corner, it had worse slack. And for the fast corner, it had the most positive slack. And so you can think of the slack as being in nanoseconds. So, this is kind of telling you we could increase the clock by 4 and it would be okay, roughly. So sometimes that's not true, but you'll have to learn that as we go. So that was the pre-place and route. So if we go in here, we can look, and there's actually also a post-place and route folder as well. So let's look at the post-place and route. And let's look at the summary report from in here. So as you can see, the summary report's a lot bigger. As this design moved through the tools, it started using more and more transistors, different transistor libraries. And if you look, still good. We had no total negative slack. So I would say anytime you open these files, the first thing you want to look for is the total negative slack. And then you can look at the setup worst slack, and you can see that the setup worst slack was like 4.38 or something for the minimum corner. So yeah, sometimes the flow's really long. It's not always feasible to run through the flow to get these results. And so essentially what we want to do is we want to make scripts. And so if I go into my scripts folder, I have some scripts in here, but only two that use tools. I have static timing analysis.tickle, and I have synth.ys. And so I can go to, I can read sta.tickle, and it's just a file that has a bunch of commands that work in STA. So this is going to read in our timing library for these transistors. It's going to read in our netlist. It's going to link those two, so it's going to map all the timing to our netlist, and then we're going to read this sign-off design constraints file, and that's going to help us also configure some of the timing. and then we're going to run through this. So if we want to see this in action, we can do make sta, and that's going to look inside scripts and read this sta.tickle script. So you can configure this script however you want, but this is how I configured it. And so when I run this script, I could see my worst slack was 3.71. And that makes sense because when I go back here, I was using this 25 degrees C 1.8 volt and it was 3.2. But you could see in this script, I used these 100 degrees C 1.8 volt and it was 3.7 for my worst slack. And so you can use these tools to essentially speed things up at times, but I recommend running through the flow when you can because it generates these really nice log files. But essentially, we can use the tools to get the same information on our own and potentially quicker. The other thing too is we can run synthesis, and so Yosis, I had you guys all run through this tool, but running through the tool and like typing everything in is really annoying. And so if we go into scripts, I have a synth.ys, and if I read that, it's kind of the same thing as the sta.tickle. It's just got a bunch of commands, and when we do make synth, oh, when we do make synth, it's going to run synthesis, and it says synthesis passed. Okay, so now we can go into our logs. And in our logs, I have all these different logs that I can generate via command, but I have this synth.log. And if I read synth.log, it's the entire output of Yosis in a log file. So you can actually see what Yosis output and see how you synthesized. And if you go into the synth folder, there's a bunch of goodies that got generated from Yosis. So here's a visualization of your design. Here's a stat on how many transistors you had. Here's a spice netlist you can use to test with. Here's a RTL IL representation if you want to check that out, and you know, some more visualization. So if we want to actually look at any of this, you know, maybe we want to look at the cell stats. So we read the cell stats.log and we can see that for our design we had 473 wires and 4,221 wire bits and 108 cells. And so we can actually look through here and look at what transistors this was mapped to. In the future, these transistors all have powers associated with them, and so we want to see again what the power of each FET is going to be, or each device is going to be. And then we can essentially map all these numbers to power and calculate what our power draw is. So as we design, we can kind of keep a close eye on what the power cost is going to be for our design, and you know, feed that to the verification team and help them make decisions. So essentially, yeah, that's Yosis and using STA as well as OpenLane. I'm gonna publish something for you guys to read to make a config file for various designs. If you guys want to check it out, I also have this multiplier example in here, and if you read the config on that, it's actually different than the config on the comparator. And so you could read the differences between the config. And here I specified die area. I also told it to skip some steps. And I put in a clock. So anyways, you guys can check that out. But for now, just use the tools, try to make your own scripts, and see if you can get some of this stuff. One thing to note is when we were using these scripts, all of these scripts had um, to include libraries for the transistors, and those are deep within the container, so they're kind of like tucked away. It's going to be hard to find them. And so I essentially made an easy command for you guys. If we go to here, and let me remove logs, and then I'll make logs. Okay, so logs is empty. If I ls logs, Logs is empty. And so what I can do is I can go make logs, and now it's finished, and I can ls logs, and it essentially has all these different log files in here. And so if I want to cat logs / open lane 2 configs, I can actually go and I can see how the environment is setting all the open lane configuration. Okay, hey, I forgot to show you guys the actual chip. So if you guys go into the examples and you go into CMP, you guys can run open lane, do the make open lane command and run through the flow. But I've already done it, so if you guys want to do make open road is our chip viewer. So we're gonna run that, and we can actually view our little comparator chip that we made. We can zoom in, we can click around to kind of see what some stuff is. Like that is a 2 input AND gate. Yeah, and there's other stuff like this is filler or decap. This is decap as well. Let's see, there's probably some filler somewhere. Anyways, but yeah, essentially, yeah, there's some filler. But essentially, this is your chip. You can go through and click around what's actually in it. But yeah, that's what the tools synthesize when you run make open lane. If you guys want to check out a bigger chip, you guys can go to the multiplier and run make open road. And you can see that this chip is much denser.